Remember, exponential growth was when we used this equation, and when b was greater than 1, that was a situation that represented exponential growth. And I even mentioned this in that previous video, but if you've forgotten, when the growth factor is between 0 and 1, the value of f of x is going to decrease. It's not going to increase, it's going to decrease. So as a result, this situation is an example of exponential decay. So the good thing is, as far as this lesson is concerned, is we're not going to have to learn a new formula. We're still going to use that same formula, a times b to the x power. Remember, a is your initial amount, and b is your growth factor. But in the previous lesson, that value for b was always greater than 1. But in this lesson, with exponential decay, that value for b is going to be between 0 and 1. And some situations that involve exponential decay would be situations involving depreciation. Anytime you buy something, whether it's clothing or a car, as soon as you purchase it, it's no longer worth its original value. If you drive a car off a lot and turn around and try to sell it, you're not going to get your money back. You're going to have to take it at a loss. And every year it's going to continue to lose value. So we call that depreciation. So let's look at this situation here. It says, suppose a new SUV costs $36,025 and depreciates by 12% each year. We're going to write an equation that gives the SUV's value when it is t years old. Okay, so first off, for part A there, we have our initial value, so we're going to write this equation. We're going to write it as, we'll use v for the value after t time. So we have an initial amount. Our initial amount here is the $36,025. Now, b is not 12%. It's depreciating by 12%. That means what's happening here is every year it's taking whatever the value was originally and subtracting 12%. So we do the same thing with our percents here. We take 100 minus 12 is 88. So that means its value is 0.88 or 88% of what it was the previous year. So anytime we deal with percents, if it's increasing, we add that value to 100%. That's what we did with exponential growth. If it's decreasing or depreciating, we subtract that percent value from 100%. And then change it to a decimal, because you never use the percents as they are. You always change them to a decimal. And then we'd have our exponent here would be t. So there's your equation. Now it says, predict the SUV's value when it is 4 years old. Also for that, you're just going to take and replace t with 4. So it would be 36,025 times 0.88 to the 4th power. And this is something you do on your calculator. So when you do this on your calculator, you end up getting a value of $21,000, or $21,604.03. So after 4 years, it's gone. You've already lost almost $15,000. I want you to try this depreciating question on your own. And so hit pause, and so pause the video and hit play when you're ready to check your answer. Okay, so for this first part, we have the value after a certain amount of time. For this piano is going to be, well, it cost originally $8,500. And it's depreciating by 6% each year. That means its value is 94% of what it was previously, to the t power. So there's your answer for part A. That's what you should have gotten. In part B, we're going to replace t with 5. And when you do that, you should get $6,238.18. So that would be the value of the piano after 5 years. Okay, let's talk about half-lives. Half-lives can be kind of confusing. This is something that's used to estimate the age of a substance. So let's write down this definition. Here's what a half-life is. If a substance decays exponentially the time it takes for half the atoms to decay into another matter is its half-life. Okay, so that's a definition of a half-life. A half-life is how long it takes for that particular substance to decay to be half of what it was originally. So carbon-14 is a common one. Carbon-14 has a half-life of 5,730 years. This means that in any 5,730 year period, half of the carbon-14 decays and becomes nitrogen-14, and half of it remains. So it takes 5,730 years, so every 5,730 years, it's going to become half of what it was originally. Suppose that an object contains 100 grams of carbon-14. We're going to let A sub n be the number of grams of carbon-14 remaining after n half-life periods. So in part A, it says how many grams of carbon-14 remain after 4 half-life periods. Well, to figure that out, there's a couple ways we could do that. One way would be to set up a table. So after 0 half-lives have occurred, there's 100 grams. After the first half-life, so that would be 5,730 years, it would be half of 100, which is 50. After the second half-life, it'd be down to 25 grams of carbon-14. After the third half-life, it'd be down to half of 25 is 12.5. After the fourth half-life, and this is what we're looking for, it'd be down to 6.25 grams. So after 4 half-life periods, it'd be down to 6.25 grams. So now in part B, it asks how many years is 4 half-life periods? Well, we know that 1 half-life, in this case, was 5,730 years. Oops. So if I want to figure out how many 4 half-lives would be, I'd multiply that times 4. So 4 half-lives would equal, if I multiply that times 4, I get 22,920 years. Part C, it asks for a recursive formula for A sub n. So to do that, remember a recursive formula, we start out with what we know for our first term. Well, our first term is going to be our initial amounts instead of A sub 1, because it doesn't represent after the first half-life. A sub 0 would represent before any half-lives have occurred, so our initial amount is 100. To find the next term in our sequence, we would take half of the previous term, for integers where n is greater than or equal to 1. In other words, for the first half-life on, we would use this formula. So an explicit formula in this case, so part D, your explicit formula would be A sub n equals your initial amount, which is 100, times your growth factor, which in this case would be 1/2, to the nth power. So that would be your explicit formula. Now it's important to represent that n in this case would represent the number of half-lives, or half-life periods, I should say. We're not going to worry about part E. Let's look at another example. Strontium-90. Strontium-90 has a half-life of only 29 years, a little shorter half-life than carbon-14. So here it says, suppose you have 1,000 grams of strontium-90. How many grams of strontium-90 remain after 6 half-life periods? Well, actually, let's solve this. Let's do this one a little bit differently. First off, let's answer part B. How many years is 6 half-life periods? Well, 1 half-life is 29 years, so 6 times 29 would give us 174 years. So a recursive formula for this would be saying that A sub 0 equals 1,000, because that's what we're starting out with, 1,000 grams. A sub n would equal, we're taking half of whatever the previous term was, so half of A sub n minus 1. Or when we're dealing with integers greater than or equal to 1. Here's the important one, though, the explicit formula. The explicit formula would be this. It would be your initial amount, which is 1,000, times your growth factor, which in these are always going to be 1/2. Anytime you're dealing with half-lives, your growth factor is always going to be 1/2 to the x power. Now, this one, we skipped in the last one, but just to touch base on it. When it says write a function for the amount of strontium-90 remaining after any real number of half-life periods x, they just want to, instead of writing it as an explicit formula, they just want you to know that the relationship between an explicit formula and a function is just that we would write it like this. Same equation, it would just be f of x equals 1,000 times 1/2 to the x power. Now let's use this to see if we can figure out how many grams of strontium-90 would remain after 6 half-life periods. So to do that, we're going to use this formula. 1,000 times 1/2 to the x period, or to the x power, where x represents the number of half-life periods. So it's going to be 1,000 times 1/2 to the 6th power. Well, when you do that on your calculator, we end up getting 15.625. So here, to find that value, we use our explicit formula instead of having to do a table like we did in the previous example. So that's half-life periods, or half-lives, I should say. So we're going to use half-lives a lot in this chapter. You do it a lot more next year in FST. This is a pretty common use for exponential decay. So let's look at another example. This one, it says, suppose a sample piece of parchment began with 100% pure carbon-14. Use the information about carbon-14 from example 2a. So we're going to use the fact that the half-lives for carbon-14 is going to be 5,730 years. That's what they're referring to. So it says, write an equation for the percent of carbon-14 remaining in the sample after x half-life periods. Well, for this one, instead of dealing with an amount, because we're just dealing with general terms, we don't have a specific amount here. So we originally start out with 100% of the material. Okay, in the previous example, we had maybe 1,000 grams or 600 grams. That was the original amount. So if we start out with, we're beginning with 100% pure carbon-14. So in this case, our initial amount is going to be 100%. Well, we don't use percents. We always change them to a decimal, so 1.0 or just 1. Your growth factor is still going to be 1/2. So our equation would equal, or be this. It would be f of x equals the initial amount, which is 1, times 1/2 to the x power. Now it's important to understand that x represents the number of half-lives. Okay, so that's part A. Part B says to graph your equation for part A and use it to find the age of the sample to the nearest century if it contains 80% of its original carbon-14. So again, these are one of those where actually we're not going to do this because I'll show you how to set it up. Again, we could solve this by graphing. Maybe in this case I'll show you how to do it by graphing, but the main idea for this chapter is I want to make sure that you understand that later on we're going to learn how to use logarithms, and that's going to be the best way to solve this type of problem. So I'll show you how to do it by graphing, but this is how we're going to set it up. We know we want to figure out how long it would take to get to 0.8 or 80% of its original amount. So it'd be 0.8 equals 1, or just 1/2 to the x power. So here's what we're going to do on our graphing calculators. Actually, before we get out our graphing calculator, let me show you what we're going to graph. What we're going to do is we're going to break this up into two equations. I'm going to break this up into the equation y equals 1/2 to the x power and y equals 0.8. And where these two graphs intersect at is going to be our solution. So let's go to our graphing calculator. So we're going to go to a graph. So I'm going to type in, again, 1/2 or 0.5 to the x power. Hit enter. And then we're going to, in order to bring up another graph, hit the tab button and type in 0.8. Hit enter. And where they intersect, that's your solution. Now to get that intersection point, what you do to go to menu and go to points and lines, and we're going to look for intersection points. And what we're going to do is we're going to select each graph. So I'm going to select this green graph. And notice how once I select it, when I move my cursor over it and hit enter, and then when I move my cursor over this one and hit enter, we get our solution. Our solution, if I can grab it, doesn't want to do that right now. Well, you get the idea. Your solution is 0.322, so we're trying to figure out what value for x they have in common, so your solution there is 0.322. But that's not our answer. That represents, remember, x, which is the number of half-lives. So if it's 0.322 half-lives for me to get down to 80% of the original amount, I would take 0.322 times the number of years in one half-life, which is 5,730. And that gives me approximately 1,700 years. So something that's gotten down to 80% of its original amount is about 1,700 years old. So why don't you try that for this next one. So this one, it begins with 80% pure carbon-14. So, well, let's do this one together. So for this one, your initial amount is not going to be 1, it's going to be 0.8. Your growth factor is still 1/2. So our equation would be f of x equals your initial amount times 1/2 to the x power. So we want to figure out, we're going to graph our answer, our equation for part A, to use it to figure out the age of the sample to the nearest century if it contains 60% of its original carbon-14. So in other words, I want to figure out how long it would take for that 80% sample to get down to 60%. So this is the equation that I'd want to solve. So to solve that on our calculator by graphing, I'm going to graph y equals 0.8 times 1/2 to the x power, and y equals 0.6. And where they intersect at, that's our solution. So when I type that in, it's going to be 0.8 times 0.5 to the x power. And the other one, hit the tab button, is going to be 0.6. Hit enter to figure out where they intersect. Look for intersection points. Select the first one, select the second one, you get 0.415, but remember that's not your answer. That just tells you how many half-life periods. So it's 0.415 for x. So again, that tells you the number of half-life periods that have gone by, but now we have to take and multiply that times the number of years in one half-life, which is 5,730. And you would get approximately 2,400 years old. So it would take 2,400 years for it to get down to 60% of its original, or get from 80% down to 60% of its original carbon-14. So that's how we apply exponential decay to half-lives. But the most important thing to remember is that we're still using the same equation, a times b to the x, but for these problems, your value for b, your growth factor, will always be between 0 and 1. So with that, good luck on your assignment.